Okay, good morning, everybody. I'm Susanna Bertelli. I'm the head of Education and Public Outreach of Frascati National Laboratory, National Institute for Nuclear Physics. On the behalf of the director Pierluigi Campana, I welcome you to the 10th edition of INSPYRE, International School on Modern Physics and Research, the school that is dedicated to the latest issues on modern physics and cutting-edge technologies. I'll give the floor to the director of the school, Dr. Catalina Curceanu.
Thank you, Susanna, and thank to all of you for being here with us this morning for this opening of our school, INSPYRE. We have arrived at the 10th edition. Of course, this is not exactly how we were planning to do it, but at least that's the most we can do to do the online edition this week. So I have prepared an introductory talk to this edition, trying to give you a flavor of what has been done up to now and what will be this week like. So it's lectures which are going to be online daily. There are two lectures per day. I'll give you some results about this and some, well, flavor of the modern physics in my introductory presentation. So as you see, our edition this year, it's entitled Hitchhikers in the Universe, because this is what we plan to do, to bring you with us in a kind of inspirational travel in the universe from the smallest constituent like the quarks up to the galaxies, dark matter, and black holes. And that's our, well, poster for this year edition, which is going to be, for obvious reasons that you all know, it's going to be online. And it's for us a very special edition. It's the 10th one. Last year, we have had here with us in Frascati about 90 students from 15 nationalities coming from 46 schools all around the world. And this year, when we were planning to organize it the similar way as last year's, namely with you here, we were planning to have, actually we have registered 100 students coming from, again, more or less 50 nationalities. And we were hoping to have you here with us. And I'll show you some, that's the photo we have done last year with all the participants which came and joined us in 2019. And usually we were organizing lectures. Part of it was lectures in our main hall. This is the guys who were here with us in last year. And one of the characteristic features was that we have, well, beyond the lectures, that was last year, quantum technologies. We will also have a quantum technology this year, by the way, but we were also doing experiments, a kind of hands-on experiments, which we were trying to do and did with the guys. Many of our participants, we were asking them for all the previous 9 editions. We were asking them what they were doing after our school. And I have to tell you that many of them, actually kind of 70% of them, are presently studying science. Majority is studying engineering and physics, and this makes us very, very happy. Some of them returned. Some of the participants which were here with us in the first edition are actually colleagues, our colleagues right now, young researchers. And for this edition, of course, due to the difficult situation generated by the coronavirus that you all know, we still want to be here with you and give you a positive message and a hope for the future and for the future of science. And INSPYRE 2020, it's here with you, and we are here with you to kind of inspire and guide you into the beauty of science. And we will give you lectures for this week, which are dedicated to the very hot topic of modern physics, like particles and cosmology. And we will give some details related with the world of the quarks and black holes, but also bring you into the world of the quantum physics and its technologies. up to the main experimental facilities from Frascati Laboratories. I'll tell you something related to this. And also it's the CERN. We will have a special lecture of what's going now in the biggest lab in the world at CERN, what's going to happen there in the coming years. So I hope that you will be with us this week, and we are here with you to inspire you. Along with this, I have prepared an introductory talk where I want to give you a flavor of what you are going to hear this week. So you are going to hear something related to modern physics. I'm going to tell you what modern physics is without too many details, because these are going to come from my colleagues. And well, what better start than everything happens in the universe for a reason. This is a very well-known slide, actually. And that reason is usually physics. So this is very famous saying. But what I want to go is beyond this and try to get with you in part of the physics items we are going to explore this week. So we have selected for you special features of physics. Part of these special physics lectures are going to dig more into the details of cosmology or quantum mechanics, like astronomy or nuclear physics. So we are going to have you with us in this exploration to the universe and to its mysteries. And before doing that, let me show you some pictures of our lab. And our lab has one of the main facilities, what you can see in this picture, which is the Daphne accelerator. Actually, it's a collider of particles and antiparticles. And this collider, it's one of our key instruments where we are doing experiments. One of them, the one which is actually on the machine, is going to be presented to you more in detail in the coming days. And we also have not only, let's say, facilities for doing physics, but also very beautiful nature. I've done these pictures last year. So this is an insect and a flower, and this is a lizard. So we also have some kind of very nice insight to inspire not only for physics, but also for the beauty of the nature. And that's a view, or the top view of our institute, which is called Laboratory Nazionale di Frascati. We are near Rome, southeast of Rome, kind of 10-15 kilometers from Rome. And this is our biggest lab of physics, actually in particle and nuclear physics in Italy. And we are very proud to host here this particle-antiparticle collider, which is called Daphne, on which you will hear much more in the coming days, actually on Thursday. And also, that's another picture of the accelerator seen from outside. And I'll go back to this towards the end of my presentation. But before doing that, let me tell you something about what is modern physics. So modern physics starts with the aim to understand what the nature is, how it works, how the universe is built, and what are the laws staying at the bottom of the universe. Not only at the universe as it is now, but also we try to answer to questions like how the universe was born and how it evolves. And what we know now starts from, let's say, more than 100 years ago, actually by the end of the 19th century, with periodic table of elements, which actually puts all together in a very logical way the world of chemical elements. We know now that we have kind of more than 100 discovered chemical elements, which are at the bottom, at the basis of the matter in the universe. So all the matter, it's built out of the known matter. It's built of this type of chemical elements, being it simple molecules like the water molecule, which looks simple. Actually, it's not so simple because it has fantastic properties. Water, it's the element of life, and as such has really fantastical chemical and physical properties. there are also much more complex molecules. That's life. The life molecule is the DNA, and it contains billions and billions of atoms linked together. We are still trying to understand how this is done and what are the properties of these molecules now, even more than ever, because that's one way to try to handle also this virus, which is, well, struggling everybody, the scientific community, to struggling with it right now for a deeper and better understanding, which helps us to deal with this problem. But we also know that we have had in the last century especially better understanding of the universe, not only as it is now, but also on the evolution of this universe, starting more than 30 billion years ago, of a process we don't know what it is, but we call it like a Big Bang. So we have a Big Bang theory, which tells us that the universe was born out of an enormously fantastic process, which actually we call Big Bang, not because we understand what it is, we don't, but at least we know something about what happened soon after, because out of our studies in particle accelerator, we do understand processes which occurred some microseconds, nanoseconds after the Big Bang, because we know how the matter was soon after that huge process which brought our universe into existence. We also have an understanding of the evolution and of the expansion of the universe, also if there are some mysteries to understand. We have some pillars, which are very solid pillars on our modern physics, and actually modern physics is defined by these pillars. And these pillars are the relativity and the quantum mechanics, which are two theories which were born kind of 100 years ago. And I don't plan to give you an introductory talk in neither of this one, but certainly you will hear more, at least on quantum mechanics, because you will have a dedicated lecture on this by one of the world experts, not only in quantum mechanics, Fabio Sciarrino, but also in quantum emergent technologies. And relativity is that wonderful theory which Einstein has set in 1905, seen as the special theory of relativity, imagining himself when was more or less of your age, kind of traveling on a light ray. So he was there in the universe trying to imagine how universe would look like. And by the postulate of the constancy of the velocity of light, he developed this theory which deals with this marvelous space-time equivalent with matter. So relation between matter and energy on one side, and space and time and its geometry on the other side. So we have here Einstein sending us from his past smile and kind of a greeting to, I hope, also thinking about us and our generation and your generation. We see here again Einstein and his fellows who developed modern physics and particularly quantum physics here. And we have here the main part of that guys who introduced quantum mechanics and its mysteries. And that's one of the Solvay Congress 1927, one of the most famous things in all the history of physics. And related to quantum physics, we have here also one of the icon of quantum physics, namely the Schrödinger cat. And Schrödinger cat, which has been introduced as a paradox, which stands for what it is right now, one of the puzzles of the quantum mechanics, related with the superposition of states, which in turn is related with the quantum technologies. You will hear some again in the lecture of Fabio Sciarrino, but I also mentioned the quantum teleportation, which is being generated right now in the labs, actually in the lab of Fabio Sciarrino. That's the lab which for the first time in the world realized the quantum teleportation at the lab level, but maybe in the future, why not? We will have something to learn more about this. So based on these two pillars, quantum mechanics and relativity, with a lot of mathematics, because the mathematics is the language of physics, it's the grammar. As a grammar, it's at the root of all the languages. When we talk physics, we talk the language of mathematics. And with this mathematics, we have developed what it is right now, the standard model of particle physics, which stands, it somehow, for many reasons, the equivalent of the modern physics. And we have here a kind of a formula of the standard Lagrangian, which is the so-called basic mathematics for the model of the standard physics, which stands for what happens in the world of the particle physics. And we don't only work with mathematics, of course. Of course, we need it, we need theoreticians, but we also need to put in practice and experiment what the theoreticians are saying. So to link what theory is predicting with what experiment it's doing in its lab. And by this point of view, I show you again a picture from our accelerator here in Frascati. That's Daphne seen inside, where we are colliding matter and antimatter. And we do so just to be able to have a kind of an introduction and a hint and ideas of what is happening in the particle world and measure, why not, new particles, new processes, trying to check whether standard model is always valid or not. In a similar way, it's not only us who is doing this type of experiments, but there is also another accelerator. That's the accelerator, the biggest in the world, is the Large Hadron Collider, staying at Geneva, actually in the border between Switzerland and France. And you see there in a red line the trace of the accelerator, not because it stands on the ground. It doesn't stand on the ground, not only because we don't want people who live in that area to go out in the house and just bump into the accelerator, but also and mostly because we have the accelerator, which is a very highly radioactive environment. So that's the reason for which in reality the accelerator, it's hosted at 100 meters underground. 100 meter means like 30 floors deep underground, and this protects us against the intense radiation which is generated by this accelerator. And who might be worried, like for example for the insects or for the worms which are deep underground, you shouldn't be too worried, because insects are notoriously known to be much more resistant to radiation. Actually, do you know which is the insect which stands the more radiation, hundreds and hundreds times more than us? The scorpions. So scorpions are very, very resilient to radiation. Anyway, go back to physics and to the particle worlds. We don't only need accelerators, but we also need particle detectors. So these particle detectors are measuring the particles which are being produced in the accelerator, and we study them in order to measure. Well, our aim is, our hidden aim is to try to measure particles which has never been seen before. But this happens very, very rarely. Usually we just measure and remeasure the same old good fellows, namely the same particles we already know. But we still struggle and hope and fight and improve our accelerator and our detectors to be able maybe to catch a hint of new physics. And I'm going to bring you there in just a few minutes, what means new physics. And before arriving at new physics, let me show you what we know up to now. So what we know up to now is that the world is done of particles. And to get there, let me show you the atoms. And atoms, what we discussed before in the Mendeleev table, we know today that they have a substructure. So actually, when you go in to dig into the structure of an atom, you discover that this is rather complicated. So an atom is a world by a universe by itself. It contains a small nucleus inside, as you might see there, which is composed by protons and neutrons, surrounded by electrons. And themselves, you might see here, so that's the atom, and the atom contains a nucleus which is very small with respect to the overall dimension of an atom. Like, let's say it's kind of 100,000 times smaller than the orbits of the electrons. And the nucleus itself is composed by protons and neutrons, and themselves contains even smaller particles, teeny, teeny little quarks. So each proton and neutron contains 3 quarks. Quarks and electrons, as we know them today, are elementary. Elementary means they have no structure anymore. Actually, you might ask me, and I'm sure somebody of you might have thought about this question, are you sure that quarks and electrons are built of no smaller particles? No, we aren't. But our accelerators are unable yet eventually to break the electrons of the quarks if they are made of very, very, very small particles. So for what we know today is that if they have a structure, this should be much smaller than 10 to the minus 18 meters as quoted there. Maybe in the future, and this might come from Frascati, I'll show you why, we might build much stronger accelerators, and we might learn whether quarks and electrons are built of smaller particles or not. Anyway, going back to how an atom is, we have here one of the simplest atoms in absolute, namely the helium atom. And if we look into it, we discover that even the smallest, one of the simplest atom, when you look into the elementary particle, it's actually rather complicated. Each quark is related to other quark by interaction, strong interaction, and themselves changes, forces and force mediators. So it looks more or less like this. But we didn't only discover the quarks. You might notice here, if you look carefully, that the proton and neutron contains only 2 types of quarks, U and D, namely up and down. But actually, in particle accelerator, we have discovered more than these 2 quarks, up and down. We know today that there are different quarks. Beyond the up and down, there are other strain, charm, top and bottom, which build up particles which are created in particle accelerator, but live very shortly. When I mean very shortly, mean like much, much smaller than 1 microsecond. They might live even smaller than 10 to minus 18 seconds. What happens when they die, to say so? Actually, they decay. They decay in more and more stable particles up when they arrive to the stable particle we know, like proton and electrons. But the starting particles might contain these quarks like strange, charm, top, and bottom. And now when we put all these elementary particles together, and that's actually how we discovered them. So when we do collisions, that's proton-proton collision in the Large Hadron Collider, you might see that it happens that in the final state, out of the transformation of energy in mass, so you remember Einstein formula, E equal mc squared. So when we collide particles, the energy, in this case their kinetic energy, is transformed in mass. And part of the mass means part of the particles in these final states are particles we know, but others are particles we discover. And that's how, for example, the Higgs boson was discovered. And going back to what I told you before, namely putting together all the particles which are elementary and we have discovered like that, we came up with what replaces today the Mendeleev table, which is the standard model of particle physics. This standard model is based on a formula I showed you before, And well, it contains this number of particles, which is quarks, the 6 quarks I told you before, electrons and neutrinos and the Higgs boson. And well, these particles are respecting, so the model is based on the quantum mechanics and on the relativity theory. And we might say, or we might be tempted to believe, that then we have a full understanding of the universe. Well, actually, it's not like that. We don't. If not for else, because in this model, there is nothing which speaks about gravity. So this model, in spite of its enormous success, speaks about electromagnetic interaction, about the nuclear forces, but it does not include gravity. Gravity, it's nothing. There is no force of gravity in the standard model. Why this? How could it be? Well, because up to now, nobody was able to build a formula, a theory, which described the gravity in quantum physics. So there is no such thing like quantum gravity. This has a long story, and I'm sure that part of the lectures in this week will touch this point. I only want to introduce you the fact that the standard model, it's not perfect. It's great. It describes electromagnetic force, nuclear, but does not describe the gravity. And that's already a problem. Already at this point, we have this problem. Gravity is not included in the standard model. Good. This does not mean that we don't understand gravity at all. We do have a theory of gravity, actually. That's the Einstein beautiful general relativity theory, which is not a quantum theory, by the way. It's not a quantum gravity theory. That's the reason for which it doesn't stay in the standard model together with all the other forces and interactions. But we do have, it's classical, so it's not quantum. We have this beautiful theory, general relativity of gravitation, and that's a theory which relates matter and energy on one side with geometry of space and time on the other side. Actually, that's the formula. I'm not going to comment it because there will be a dedicated lecture, I think it's Friday, by Viviana Fafone. She will speak much more in detail about the gravity and the beauty of gravity and research which is being done in this field. But though I want only to tell you that this formula has a beautiful feature inside. And the beautiful feature inside is the sign, which is the equal sign between this right term and left term. Why is this? Because on the left term, we have everything which is only geometry, space-time geometry, which, which is related with, I repeat, space and time, while on the right side, we have everything which is related with matter and energy. So means stars, planets, dust, and whatever else. So geometry, it's equal with matter. And John Archibald Wheeler used to read this formula saying that matter tells to space-time how to curve, so the geometry defines the geometry of space and time, while space and time tells to matter how to move. And that's more or less in this cartoon. So matter creates the geometry, and then matter itself moves in this new geometry according to Einstein formula. And this is a very, very, very successful formula. Even light bends and travels in the universe according to the new geometry defined by the geometry of the space and time, defined by the existence of matter in the universe. And this formula, it's enormously successful, but it has a limit. It has a limit because it defines, let's say our sun is deforming the geometry very little because the density is not so high. There are much, much denser stars like the neutron stars you see here, which by the fact that they are so dense, we will have a lecture on a Thursday related with neutron stars, by the way. and they are deforming the geometry much more. But at some point, when you go beyond the threshold, happens something very awkward, very strange. It happens that the Einstein formula breaks down. And this happens when we speak about the black holes. So when the density goes beyond the threshold, the deformation of the geometry goes to infinite. The formula does not succeed to account for what happens inside this type of objects. So, which means that we have a singularity. It's called a geometrical singularity, which also means that the gravity inside this, it's infinite. And that's, well, it's where the gravity, the general relativity, breaks down. So we don't believe that in the universe really gravity becomes infinite. It only means that even the beautiful theory of Einstein breaks down. It's not valid anymore in these conditions. And we have no idea what's the theory which might be valid inside. Well, actually, it's not quite true. There are some proposals like the string theory or the quantum loop gravity, but we don't know whether this is something which it's true or not, which they are really theory which are valid or not. So basically, we are left with the unknown world of the inside of a black hole. Well, we need a new theory to describe what happens inside. And not only a new theory, but we also need experimental insight. And this experimental insight came lately from these beautiful experiments like the gravitational waves. So this is a gravitational antenna, LIGO, on which you will have a dedicated talk on Friday, which succeeded to see these waves which are created in the space-time structure generated by colliding black holes. And it is assumed that if we would be able to measure or to refine our measurement of the details of these black holes, we will also have information correlated with the black holes itself. So that's what this gravitational antenna succeeded to measure. You see these waves which are coming, propagates along the space from a billion of years, light years far away, coming and arriving here and making resonance, making the interference on this antenna and get up to here, up to us. And of course, somebody might wonder how this, what would happen to us if we would jump inside a black hole. This is a very legitimate question, but we don't know the answer. We have some hypotheses, which are scientific hypotheses. Some of them are very, well, more like science fiction, and some of them are seeing, well, by the way, one should be very careful which are the black holes we might select to jump into, because if the black hole, which is the one which select it's small, like 10 times, 100 times the sun mass, what will happen to us is not very funny, because it's going to happen spaghettification, meaning that gravity is so intense that our body would be spaghettified. So at least this is a message to the hitchhikers who might reach a black hole. Don't go towards a small one, but select a very big one. Because in this case, since the gravity at the border, namely at the event horizon, is not very high, dear hitchhikers in the universe, nothing will get like spaghettification. We might get inside without problems, and there are black holes as big as billion times the sun mass, which means that they are huge, 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 and some of them are staying in the actually in the center of our galaxies. And well, in this case, what could happen to us, and the physics allow this, it doesn't require, but it might allow this, to make an interstellar travel, which means that we might go inside a black hole in our galaxy and get to other galaxy like in no time, because we would get the shortcut in space and time generated by the black hole. Of course, we don't know whether this is true or not, but that might be a possibility. And there is even something more exciting, which has been said by one of the maximum experts in black holes, Stephen Hawking, who even dare saying, and if he said it, I can only repeat it, that black holes are passage to other universes. So about the black holes, if you wonder more details, please stay connected and follow together with us the lecture dedicated to this and to wonders of the space-time and black holes, which is going to be given by Viviana Fafone on Friday. And well, to understand the black holes, we have to go beyond the Einstein theory. Beyond the Einstein theory, what we believe could be is the quantum gravity, a new theory of space and time. And we are still looking for this theory. We don't have it yet. And probably, hopefully, some of you might join us in the effort to look for this new theory. But, well, the black hole interior, it's not our only mystery. We have an even deeper one. Apparently, the matter in the universe, including the black holes, it's only a little part of the budget of matter and energy in the universe. You might have heard about these dark quantities like dark matter and dark energy. And I'm going to give you a very short lecture introduction, some minutes introduction of reasons of dark matter and dark energy. And then because you will have a lecture on this by next days, including the Large Hadron Collider and more details on Large Hadron Collider and Standard Model. But though, I want to tell you why we believe in dark matter and dark energy, which are the grounds, which are the roots staying at the basis of this. So let's start with the first dark entity in the universe, namely the dark matter. This story of dark matter started very, very slowly. Actually, it started from a precision measurement. And the precision measurement in this case was the precision measurement of the speed of rotation of the stars in the periphery of our galaxy. So we have stars, they are rotating in the periphery of our galaxy, and we could measure this velocity. And we can measure it with very high precision, but we can also calculate it because the speed of these stars depends on gravity, on the gravity pool, gravitational pool of the rest of the galaxy. And we believe we know what stays in our galaxy. We believe that it's made of stars and dust and planets and black holes. So we start and we calculate. Okay, now let's compare the two. We have what we measure and we have what we calculated. What we get here? Wow, we get something which looks very weird. Namely, we have a calculated value, the red curve, which goes down because as far as we go from the center of the galaxy, the gravity pool diminishes. While we measure stands still very high. So they don't match, which means that, well, either the gravity formula we used is not correct, and there are some theories which are claiming this, but for reasons which I have no time now to explain in detail, we are convinced of another alternative, that the visible matter, it's only a small quantity of a much, much more higher quantity of matter, which is dark. Actually, it's called dark matter, but actually it's invisible matter, which is an halo of dark matter surrounding our galaxy, much bigger than our galaxy, which is called dark matter. And that's what we are right now calling dark matter. So it's felt by its gravitational attraction, which it's there because we measure it, but we don't see it because it does not emit light. So that's why it's called invisible, actually dark, because it doesn't emit light. And we are searching for it. We are searching for it in particle accelerators where they collide particles, and we hope that some of the popping up particles, like similar to the Higgs boson, might be a particle which never has been seen before, like a dark matter particle. And you will learn more about this in the lecture, which is centered of Large Hadron Collider, which is going to show you how they are going to hunt the dark matter particles. But there is even a more subtle mystery in the universe, one of which we need you, because we have very few ideas of how to measure it, actually how to measure what it is. That corresponds to what it is called dark energy. And to understand it, let's start again. We know that the universe is in expansion, so universe is expanding. It was believed that expansion is kind of a uniform. But with big surprise of physicists, by the end of last century, it has been discovered out of these beautiful measurements of high-Z supernova. So by the measurements of the expansion of the redshift, actually, of supernova far from us. So when you measure its redshift, actually you measure a velocity, then you can measure the expansion rate, and you can check your hypothesis whether it's constant or not. So what it has been demonstrated, and that it's very thrilling, caught us completely unprepared, that the expansion of the universe, it's not uniform. The expansion is accelerating. So there is something in the universe which cannot be gravity, because gravity is pulling it back. So it looks like anti-gravity, but it's not anti-gravity. That's, we call it dark energy, which is pushing the universe to have an accelerated expansion. And that's one of the biggest mysteries of present-day physics. What is this dark energy? We have some ideas. It could be the vacuum quantum energy, or it might be something which looks like a Higgs boson field, but it's not Higgs boson. It's a similar but still different field, kind of a quintessence. But we have not so many ideas how to test experimentally this. So it's plenty of free space there, guys and girls and guys, for you to come here and help us out of these big mysteries, dark matter and dark energies. But look here, when you wonder how much dark matter and energy is in the universe, we come up with something which is really, really, really thrilling. Normal matter, the one I told you before, namely the one which composes the atoms and the planets and the stars and even the black holes, it's composing 4% of the universe. All the rest, unless we are completely wrong, it's composed of dark matter, 23%, and 73% of dark energy. Well, that's really, really, really something very, very weird and absolutely to be dealt with. So we need to understand what this is. Good. And more or less, this is what type of research we are doing in modern physics, and also in my institute, in a Frascati Laboratory, and also in INFN, which means Istituto Nazionale di Fisica Nucleare. And I take this opportunity also to tell you some words about our institute, because I might hope, and actually I would expect that some of you might still come, even if not in the occasion of this INSPYRE edition, but I might hope you might come to visit us and work with us, and why not join us for your PhDs or to come and do some research with us. So let me tell you something about the history of my institute. I don't know if you have recognized here someone, any of this guy. But I can tell you that here it's Enrico Fermi. And this is in the 30s when in Italy the physics, nuclear physics, has been started by these guys who were called Ragazzi di Via Panisperna, the guys from Panisperna Street. And they were starting to do experiments in nuclear physics, the first neutron activation experiments, and they have set the ground of physics in Italy. And after this, so that has been in the 30s, then it was the Second World War, but soon after, what happened was that in the early 50s, 4 universities sat together, like Milano, Torino, Padova, and Roma, to join their efforts to do something more. So something more has been to do a lab where to have infrastructures. So the infrastructures are like colliders, so accelerators, and these accelerators are started in Frascati, actually in the lab which I'm talking from. So I'm right now here in Frascati in this beautiful laboratory, and I really hope you may come to work with us and join us in the future. And this has been actually set up in the late 50s. Right now, the institute, which is INFN, actually has not only our lab from Frascati, but has labs in Italy, which are in also in north, namely in Legnaro, south, which is in Catania, doing research in nuclear physics. And moreover, there is another lab in Gran Sasso, which is actually a very strange lab. It's underground, under the mountain, where it's a lot of research done with dark matter, neutrino, and also quantum physics. So that's our institute today. And when I go to tell you something more about our lab in Frascati, what we do here, it's basically what I tried to tell you before. So we do fundamental research, which is well, I've seen that somebody was asking whether you can come to work with us or join the institute. Yes, you can come to work with us or join the institute. Just keep in touch with us and we may provide you information how this can happen. We have fellowships for students. We have also different type of fellowships for PhDs, postdocs, and things like that. Let me go back. So what we do here is trying to answer unanswered questions I showed you before. And these are, what's the matter structure, including gravity? So can we set up a theory of gravity? Can you understand where dark matter and dark energies are? And also, we try to study gravitational waves and understand better also black holes and the universe structure. And also, we have a team which is doing development of theoretical models, like quantum gravity, I told you before, or like what are the candidates for yes, the information would be on our site. I see another question. Yes. And theoretical models like supersymmetric theories, which kind of give an answer of what dark matter is. They are supersymmetric particles, like brothers and sisters of particle we know, which are much higher in mass, and they are planned in the universe, but they don't emit light. We don't only do theory or research of this type, but we also build instruments. And our instruments are detectors, particle accelerators. We also do biomedical research, which stands for tumors, for example. We are trying to understand how tumor occurs and how do it develop. And we also have a very strong department on computing physics, on artificial intelligence and nets, which we are using. And that's again a view of our institute, where we have here our main facility, our main particle collider, particle antiparticle collider. And we also have research in accelerator technology beyond the present accelerators. And let me show you some more. I also have to tell you that we are very happy that I don't know how many of you know actually that the particle-antiparticle colliders were born in the world here in Frascati. In Frascati, for the first time in the world, the first antiparticle-particle collider has been actually realized. And this has been ADA. And I'm going to tell you more in detail this story Thursday, when I'm going to tell you something about the neutron stars and how can you study the neutron star in a particle-antiparticle collider. And we had along the years also other accelerators like Adone, which is very nice and has done the history of the Standard Model. Presently, we have Daphne, Daphne Collider, where we do experiments trying to understand mysteries in the particle-antiparticle and in the universe. We also contribute to other accelerators, so not only in Frascati, but our expertise extends to accelerator elsewhere, like those in Geneva, like well, Large Hadron Collider. And I'm showing you again our beautiful accelerator, Daphne. And that's my group, my collaboration, which is called Siddhartha, which is now, actually, now we are stopped due to obvious reasons. But we are just in experiments which are studying the structure of possible structure of the neutron star. And if you want to know more about this specific item, I ask you to join me on Thursday, when I'm going to give you a lecture exactly dedicated to this. We have had another beautiful experiment here, which took data until a couple of years ago, which is called Chloe. And this experiment was trying to answer to one of the beautiful questions you might ask to the universe. Where is the antimatter? So the universe is done of matter. There is no trace of antimatter in the universe. But we believe that during the Big Bang, equal quantities of matter and antimatter were born. So what happened to antimatter? Where is it? And we have discovered, also with the help of this experiment, Chloe, that actually there is a trick there. The laws of physics in matter world, so for particles, are not exactly the same of the laws of physics in antiparticle world. There is an asymmetry. So Chloe experiment was working on this and in many other items, answering again questions related to the fate and evolution of our universe. We also have a very, very beautiful facility, which is called synchrotron light facility, where we kind of use a kind of a microscope, but it's not the usual microscope which we use in a biological lab, but it is much more powerful. It's able to see details, teeny details which are unseenable to microscopes in the lab. And we can study evolutions of tumors, for example. We might understand material structures and graphite structures and many other things which are invisible to normal microscopes can be seen with this synchrotron light radiation. And also, we are having a strong team here which is working in the future accelerator technology. Because of course, it would be very nice if we would have, well, that's more or less what they do. So they actually work on the plasma, and with this plasma technology, they try to replace what it is a normal magnet. We use now magnets which are very big and consuming a lot of electrical power, so expensive. And that's the reason for which Large Hadron Collider is so big, like 27 kilometers of circumference. We try to replace these magnets with something else. And we have a team here which is using the plasma accelerating technology to try to do a magnificent thing. This magnificent thing is to build an accelerator on a chip. So it would be something which would bring the whole Large Hadron Collider and squeeze it from 27 kilometers to something like 10, 100 meters, which would be an obvious gain of everything. We would have the same power, but in a hand, or let's say in a tabletop accelerator. And this has been seen to be rather successful. So we don't have yet this accelerator in our hands, but still we are working on these technologies in the hope that in the next 10, 20 years, we might have this type of technology, not only to study dark matter, but, and even more, for the hospitals to cure the tumors, because we know that these accelerators used with proton and carbon ions might cure, and they actually do, tumors much more efficiently than radiotherapy. So it's useful not only for fundamental research, but, and moreover, for curing the tumors. And the same accelerators, like I told you before, here, you might see here, like using beams of particles to see teeny details which can't be seen in the optical microscope, can be used for another thing, which is very modern, like mammography. So there are beams of particles, in this case of very monochromatic radiation, again to be used for medical diagnosis like mammography, and get it much more successful than the present technology. Also, we might use it as a very sharp instrument to see how a protein is being done. And you might know that right now we have a problem with the proteins and also with the structure of this coronavirus, because we don't really know all its details, especially in these details of the proteins which it uses to attack our body. And so this research, which comes from fundamental physics, it brings all the way along, not only for dark matter, but also for things which are very, very actual day things, like trying to understand how these viruses are working and how the proteins are working and are folded, because the three-dimensional structure of a protein, it's still something basically mysterious for many out of the thousands of proteins out there. And well, now I'm reaching the end of my introductory talk to this edition of INSPYRE 2020. And what I want to end up with, it's a kind of promo for our program. So now we are in the middle of, well, towards the end, sorry, of this first presentation, like Hitchhiker's Guide to the Universe, by giving you, as a director of this school, the welcome to this edition. And I can tell you that soon after me at midday, we will have a very fascinating lecture by Amedeo Balbi, who's also a writer, not only a great physicist, but he's also writing for Science, Italian edition, related with the search for life in the universe. Tomorrow, again, between 10:30 and 1:30, we will have two very different talks. One has to do with quantum physics, the second quantum revolution given by Fabio Sciarino, one of the main experts in quantum physics, followed by a theoretician working on the time. What is time? And he will try to give some answers on this absolutely fascinating question. What is time? Lorenzo Maccone from Pavia. On Wednesday, we will have a full immersion in biotechnologies with two lectures given by two experts, Stefano Bellucci and Antonino Cataldo, giving us an insight in one of the modern features coming out from physics, but extending bio-nanotechnologies and their applications. And in the last 2 days of our lectures, we will have on a Thursday And I take this opportunity to also thank our chairs. You might have that each day we have a chair, and I thank from the bottom of my heart to my colleagues for helping me to chair this school. So Thursday we will have something which is related with the gravitational waves by Viviana Fafone. She is the Italian responsible of the gravitational antenna program. You see here gravitational waves in the next decade, so by when some of you might reach us, and followed by a lecture from me related with neutron stars and strangeness in the neutron stars and how can you study this with particle accelerator. While in the last day, we will end up with this physics at the femtoscale, where Friedrich van der Weken from CERN will give us an introduction to LHC physics and to its program, bringing us in a dream world for the next years. And last but not least, we will have Matteo Martini from Frascati Scienza and INFN and Marconi University talking about a very, very modern topic. What it is the 21st century news jungle, how to get out from the jungle, from the food for thought to survive. So how can we survive in a world of fake news right now? And I conclude by doing not only my duty, but my big pleasure to thank to knowledge and thank to all the INSPYRE team, which has contributed. You might not see them on video, all of them. You have seen them if you would have come here. All this beautiful team of our girls, Sara Redda, Camila Paola Maglione, Sara Arnone, Deborah Bifaretti, Elisa Santinelli, Elena Patrianelli, and Susanna Bertelli, who is chairing this session. You see them in pictures here. And girls, thank you very much for doing this possible. It would never be possible without you. And also, let me thank you, our media partner. If you see me now, and if you will see our colleagues, this is thanks to our media partner, Frascati Scienza, who is not only allowing us to use their platform, but it's also assisting us to be able to give you these beautiful lectures. And last but not least, let me thank to all our sponsors, like European Physical Society, Foundational Questions Institute, Società Italiana di Fisica, Centro Fermi, the Nuclear Physics Center, and the European Strong 2020 project. And then I hope you will come sometime to Frascati. That's a picture, a photo of the Frascati town, where if you couldn't come this year, I really hope you, the guys who were enrolled in INSPYRE, and all of you who are looking at us right now, I hope you will come and visit us, not only in the town, but again in our institute. And I conclude telling you that physics, it's a never-ending story. We are now having a solid physics, but we are also emergent signals of a future which is unknown, which might be quantum gravity, dark matter, dark energy. We don't know. It's up to you and up to us to have to be able to answer these really, really beautiful questions. And I hope that by the end of this week, we will be able to be your guides to the universe, your hitchhiker's guide to the universe and to the beauty of this end. And here I stop. And if there are questions, I would like to kind of ask you if you have some questions. So I'm now looking at your questions, and let me see if there is anyone who has. Of course, that don't be afraid if you didn't understand details, because my aim was not to give you details. It was an overview of what you will have along this week, to try to encourage you to stay with us as much as possible during this week lectures. And yeah, as my colleague, it's reminding you and reminding me, all our lectures which are going live will be also saved on our YouTube channels. There are 2 YouTube channels, the one of the lab, so the INFN LNF lab, and the one of Frascati Scienza YouTube channel. So you have 2 chances to look at us and to follow us, not only live, but also during the... And let me give you some sentence in Italian. Tutti quelli che ci hanno seguito dall'Italia, vi mando un carissimo saluto e spero che tutti voi ragazzi, sia quelli che hanno partecipato, che dovevano essere qua con noi in questi giorni a partecipare a INSPYRE di persona, io spero che verrete comunque a trovarci e spero anche che tutte le scuole, ho visto parecchie che ci state seguendo, riuscirete a seguirci questa settimana. Vi mando un caloroso saluto non solo ai ragazzi di INSPYRE, ma anche a tutti quanti ragazzi di tutte le età ci state seguendo in questo momento, è momento abbastanza difficile. So now I see another question. When more on dark matter, there will be more on dark matter in the lecture given by, let me see when this lecture is going to be, by Frederick, which is going to talk in his lecture on the last day lecture, Friday. So Frederick van den Wecken is going to speak on the dark matter, including searches of dark matter. Yes. And yeah, sorry for, I had to speak a little bit in Italian because I know many people, yes, sorry for those who were, I've seen that there are guys from Portugal. Actually, you were the first one to, the first one you connected. Hello, Portugal. Hello, Iran. And if you can tell me, where are you coming from? Oh, there is a question I've seen, why we collide at LHC protons and non-particle and antiparticles. This happens because the energy in this case, the kinetic energy of the protons, it's so high, hugely with respect to their mass, that the additional energy brought into game by the mass of the particles when they collide, it's really to be negligible. So what matters is the kinetic energy. And since it's easier to accelerate protons, we used to collide protons because their additional mass does contribute almost nothing with respect to the kinetic energy. Hello, Iran. Hello, Portugal. And I'm really happy you succeeded to join us. Really very happy. And from Shiraz. Hello, Shiraz. And from Italy, where are you guys connected from? Italia, da dove vi siete collegati? I have seen you before, but I don't have you just under my eye right now. If you can tell me, where are you? So France. Bonjour France, je vous salue. J'espère que vous verrez ici à Frascati. Yes, Portugal is very, oh, New Zealand. Wow, that's great. Hello, New Zealand. Udine, buongiorno Udine. Oh, wow, that's very nice. Roma, siamo vicini di casa. Grottaferrata, hello Grottaferrata. Piedmont, hello Piedmont. Milano, oh Milano, heart with you. Il mio cuore è con voi. Cosenza, Roma, che bello. Lecce, Frascati, Roma, di nuovo. Bologna, Bracciano, Lodi. Lodi, non un posto felice. Yeah, you're right. I'm with my heart. I have to send special greetings to all the people from North Italy, especially from the people from you know, you maybe everybody know Torino, Pisa, Reggio Emilia. So Reggio Emilia, and especially the people coming from northern part of the Italy are deeply hit by coronavirus, are deep into my heart, and allow me to give you a big hug. So Bracciano, Frosinone, How can we get protons out of nucleons and manage to make them collide? Great question. So actually what we do, when we use an accelerator, we have initially an electron collider. It's a complex of accelerator. So to get beam of protons, we initially have an electron beam, which is easy to get because it's enough to hit a wire. Then you get electron beam, and you hit this electron beam into a foil of metal, tungsten. When you get that, this extracts secondary particles, among which protons. So that's how you are forming a proton particle. So proton beam. Luigi Trafelli, i miei carissimi Luigi Trafelli, Frosinone, Nettuno, Cosenza di nuovo. Valeria, saluto. I'm really fond of your child, 7 years old. Mwah! I send you a lot of yeah, Salvatore is asking if coronavirus. Correction. Salvatore, va bene. Why dark matter cannot be seen? Because it doesn't emit light. Why it doesn't emit light, we don't know. Because we don't know what it is made of. Are we in touch with NASA for more research? Yeah, part of our institute, it's connected with NASA, and they are actually performing research in collaboration with NASA. Actually, on the satellites, they are doing some devices for getting more information. The meaning of Daphne. So Daphne means a double annular 5 factory for nice experiments. If you can have slides for your presentations, well, you will have the presentations online. If any one of you want to have the slides, it's enough to send me a mail. You can find my email more or less everywhere, and I can send them to you easily. So don't worry, I can send you the slides, and probably we will also set the slide on our programs, so you can directly download all the slides from our. How can we measure the size of a black hole? Well, that's a very nice. Please keep this question for Viviana Fafone, who will directly talk on this Thursday. So you can ask her. She's an expert of black hole. So Puglia, saluto Puglia. Vedo, I'm seeing a lot of greetings from Italy. Should we confirm our presence somewhere? Yes, you will receive the ones who are participants to INSPYRE School will receive their certificates, their participation certificates, and even if there is some guys of you who might need the certificate for participation, so the award for participation, let us know, send us a mail, and we will provide you this. So I've seen somebody, actually Paris K was asking about this. So just let us know, send us a mail. You find all the information on INSPYRE 2020 website, and you can see that in our poster. It's easy to see that. So, di nuovo, Puglia, when we will be able to come again to visit INFN? Well, guys, I really hope soon, and I hope already from this summer. But you know, we have to deal first with this problem, which I hope will be over soon. Veroli near Frosinone again. Many greetings, guys, and please follow us. If you have nothing better to do, just be with us these days and keep in touch and let us know what you are thinking and what you, if you have questions. The other sessions will be organized differently. We will do 15 minutes lecture, then we will dedicate 5 minutes to questions, such as to make it a bit more lively. So I thank you very much, and a virtual hug to all of you. If I have any note, not really, but again, for whatever you might wish, or if you want something more, just get in touch with us, and we will be happy to help you or provide you whatever it's in our power to help you to enjoy the most. Lampedusa, ciao Lampedusa, to enjoy these lectures and to make them as fruitful as possible and allow us to dream in these very difficult moments. Dreaming, it's very important. And I think that science, it's one of the great things which help us dreaming. Yeah, I think we are reaching our end of this introductory lecture. Please stay in touch, and at 12 o'clock, we will have the lecture about the search for extraterrestrial life and for, yeah, with the question, where is everybody? See you soon. Enjoy the rest of the day. Bye-bye, guys.